Archiving started.
Okay, everybody's attention. Today, we're going to have somebody new who's never given a talk in this series before. And this is Guy Hilburn. He's a graduate student at Rice University working on his Ph.D. Should be done within the next year. And actually what happened was I actually saw a copy of his paper that he had published on this, and I thought, this is some really interesting stuff. And I thought this would be a really good thing for our series. And a lot of what he's talking about is actually using a GRMHD code, which I've been interested in, as which is basically a code which looks at relativistic plasmas and general relativity in order to do some really cool, interesting simulation work. So with that, I'll turn over to Guy.
Right. Thank you, Dr. Garrison, and thank you all for being here today. I'm going to be talking about my work with Dr. Edison Liang at Rice. This is my research. I have my master's now, will be getting my PhD in about a year, and I've put together a presentation that pretty much encompasses everything that I have done throughout my Rice career. What I will be talking about my work is simulations of low luminosity active galactic nuclei. And I know that we're all coming from a number of different walks of life, so I threw up a couple pretty pictures here to start out. On the left, this is just an artist's rendition of what an accreting black hole might look like. And the idea in this situation is that we have a main sequence star here losing matter onto a black hole. It falls into a disk, which is falling onto the black hole. The disk radiates because of the conversion of gravitational potential energy to radiative energy. And then these outflows along the pole of the rotating black hole are jets, which happens whenever the magnetic and gravitational energy is converted into outflows at the polar regions when the accretion disk reaches the black hole. The picture on the right is a 3D GRMHD, general relativistic magnetohydrodynamic simulation. And I just chose this one because it shows in the middle you can see just this tiny accretion disk and then very large scale jets coming out. The lines that are shown are magnetic field lines. And this is just a density plot in general. Now, before I really get started talking about the modeling, I thought it was important that we all kind of touch base on what low luminosity active galactic nuclei are. AGNs are usually related to supermassive black holes at the center of galaxies. They're called active because they tend to be extremely radiative. As I've pointed out, the main reason that these are called low luminosity AGNs is because they're very radiatively inefficient, which means that whereas the maximal possible efficiency for an AGN would be somewhere along a few percent, that is a few percent of the energy of these particles would be radiated when falling into the black hole. In this case, because of the radiative inefficiency, most of the radiative energy is lost to the black hole before it's allowed to be released. The most famous and well-studied of the low luminosity AGNs is Sagittarius A Star, which is our galactic center. It's located about 8 kiloparsecs away, several million solar masses, so definitely a supermassive black hole, as we would term it. We have a number of multi-wavelength observations on it. Some of the bands are difficult to observe our galactic center with because of the dust and such between us and there, but we have a great deal of these multi-wavelength observing campaigns which have been used to constrain things such as the black hole mass, the black hole spin, and then various parameters for the accretion disk around the black hole. And I just noted here really quickly that there are energy flares radiative flares happening in this environment. And one of the reasons that I have not said anything about a jet system with this AGN is that it does not have a very efficient conversion of energy into a jet system, and we don't see a great deal of activity that we would relate to a jet. The way that we can tell this is by looking at multi-wavelength observing campaigns, seeing where radiation is flaring or when radiation is flaring, really, and then computing what the actual size of the emitting region would be based on the amount of lag between different components and such. This is a spectral energy distribution for Sagittarius A Star. Up at the top, I've just noted very rudimentarily the radio, infrared, and X-ray bands. So it'll be obvious whenever I'm talking about one or the other. The points on the left here in the radio are actual data points. The upside down triangles here are upper limits. And then the bow ties out here indicate a flaring and a quiescent state seen in the X-ray. So at one point, the spectrum for Sagittarius A Star went straight through this upper bow tie with a flat, with kind of a flat slope there. And then at a quiescent state, sometime later on, it went through this lower bow tie with more of a sharply peaked slope at that point. And this is very interesting, seeing how these points have different slopes, because that indicates that the component that is making the emission at that region must be flat, first of all, and then whenever something happens to shift the luminosity lower, it has to be sharply peaked. And that only leaves several possibilities for what that emission mechanism might be, which I'll get to soon. Oh, I should note that the flare correlation, like I was saying before, the temporal correlation between the flares of different components, say if you had a flare that happened in the radio at the same time you had this flare that happened in the X-ray, you could say those were correlated. And because of that, the assumption, the usual assumption that this is a synchrotron curve, due only to synchrotron emission, would suggest that this flaring point would also be due to synchrotron emission at some point. And I've just theorized here that that would be SSC, or synchrotron self-Compton emission, that is, upscattering of photons, of synchrotron photons by the population that produced them to higher energy. Another very famous LLAGN is M87. This is about 1,000 times bigger than our galactic center, and it's very well studied because of its proximity to us. And it happens to be aligned in such a way that we see this spectacular kiloparsec scale jet coming out of it. And because of that, we have a very simple time in comparison to most AGNs, looking down at the jet forming region, seeing the relation between the jet and the accretion disk, and so forth. In this case, the multi-wavelength observing campaigns have shown that the X-ray, the very high energy flares, have been correlated at different times to both the disk and the jet. So it's you can't just say that the X-ray emission, for instance, comes from the jet and the VHE comes from the core and so forth. It's an entire system tied together. This is an example of the core spectral energy distribution for M87. And it looks similar. You see what we would expect to be a synchrotron curve at low energies. This is really more in the IR. This would be the X-ray point. And then we have some very high energy points out here, including a flaring and a quiescent set. And this flaring set, the one on top, I think it's in green here, correlates with this bow tie. And in this case, all the jet data has been subtracted from this. So this is just an SED for the core. Now, moving on into the simulations that I do, the primary simulation tool, the main simulation tool that I use is the HARM GRMHD code. It's a 2D axisymmetric code, which means that it's laid out in 2 dimensions in the radial and vertical direction, essentially. And then everything is assumed to kind of reflect all the way around what we would call the axis of the black hole. So what we're looking at here with this plot is a density map. The red points would be the highest density, the dark blue, the black points would be the lowest densities. And so this would be a cut through of what we would term the accretion disk. The reason that it looks less like a disk and more like an oblong object here vertically is just because of the scaling of the code. It is more concentrated, the cells for the code are more concentrated in the equatorial region, as well as close to the horizon. And so we get a lot more resolution at those points. We put together a library of results using HARM, which include black hole spins from 0 up to nearly maximally rotating black holes. And this will allow very easy comparison between those physical parameters and the final radiative results. As I've noted here at the bottom, the grid size in this case, depending on what we scale the eventual result or data to, is usually 10 to the 10th to 10 to the 15 centimeters or so. It's not a uniform grid size, which is why there's such a large range in that. But you can see that these are fairly large spaces that we're considering if each of the cells in this grid is 10 to the 15 centimeters. Now, this is a picture, a composite picture from Hahn, which shows on the left a run done with a black hole spin of 0, and on the right a run done with a black hole spin very near 1, which would be the maximally rotating black hole. And on the top, we have plotted magnetic field squared, and on the bottom, the Lorentz factor of the accreting gases. And so what is of interest here is first looking at the geometric considerations. Like I was saying, we're spaced closer to the equator and horizon. So you could see this 8m mark, which would be a radius based on whatever you set the black hole mass to, is halfway up to this 40m mark. So you can see this is a logarithmically spaced area. And also on the bottom, I've noted the opening angles for each of the two different cases. But you can see that this obviously does not look like a 30-degree space, and same for 37 degrees here, because these cells are tighter close toward the equator. But that's just to give an idea of what the actual spaces we're dealing with here are. What's of most interest in these cases, or at least comparing these two cases, is that you would have definite outflow formation along the pole here for the high spin case. Whereas for the low spin case, it is much less noticeable, and you even have points where they have a floor value of the Lorentz factor, which means those regions are moving very slowly. Whereas in this case, we have Lorentz factors of around 18 or so, which may be 99.9% the speed of light. The magnetic field on top, you can see that it becomes very turbulent. This is at a late time in the simulation, and this happens regardless of what the spin is, though the regions close to the equator do tend to be more interesting for the high spin cases. Feel free to stop me if you have any questions throughout this, or if I'm going too quickly. Now, I wanted to briefly mention the magnetorotational instability, because this is what we now expect to govern a large portion of the angular momentum transport in accretion disks. One of the long-standing problems in modeling accretion disks was that we did not have a good explanation of what people term viscosity for a long time. And they would just use a simple parameter and say, this is a viscous fluid of some level, and use a number between 0 and 1 to explain that. Now we know that because of the magnetic ties between pieces of accreting fluid, there is an easy way to explain the transport of angular momentum out of a disk. That is, as material is accreting onto the disk, the angular momentum has to be conserved, and so there's no explanation for how, if a chunk of matter just falls straight into the black hole, what happens to its angular momentum. In this case, if we look at these two accreting pieces of plasma, say this is the first step, and then just displace them slightly from one another at a slightly further point in their orbit. What would happen in this situation is that the smaller, or the closer end point would want to fall inward, but it's being tugged back on by the magnetic connection between these points. And that would slow it down, which would in turn encourage its fall further into the black hole, which you can see at this point. And vice versa for the piece that is further out, the magnetic tie would tend to speed it up, which would displace it even further from the black hole. So you can see in this case, despite the intense gravitational potential here, we have a case where a piece of matter has to essentially fall out of the black hole in order for one to fall in. And this governs, like I said, the angular momentum transport on the disk. Now, the most interesting part of the talk, the pretty movies. On the left here, I have a density plot. You can see at very early time, at very early time, we just have a torus here that is set up around the black hole with no disk formed yet. These are obviously not timed up anymore, but you can see this plunge happened at the same time that the magnetic field plunged in over here. This is a low spin case. So you can see how the magnetic field fills out the area. This is run to about 8,000 time steps, which would be physical time for the black hole, which for something like Sagittarius A Star would scale to about 100,000 seconds that we see this going on. You can see the large development of turbulence as this continues on, the kind of sharp infall, which correlates with stronger outflow along the poles. And I guess it's restarting. Now, to put more numbers on these situations, looking at the harm output and some physical values that we get from this, this is all already scaled to a black hole mass and such. In this case, these are all normalized units, but it gives you an idea of how things scale with radius from the black hole. So this says radius in units of m, so the black hole horizon in this case would be at 2m. You can see that everything cuts off there. Obviously, the numeric simulation does not really go far beyond the horizon. And of interest is how turbulent the magnetic field is primarily, and how closely what I've termed the synchrotron emission follows that magnetic field. And then also this region very close to the black hole. I talked previously about the plunging region, the advection zone, where most of the material just falls straight onto the black hole. It loses the ability to radiate significantly. And you can see at this point that the density and temperature do drop significantly once they get within about 6M, and that's really the point where everything just starts funneling straight into the hole and does not radiate greatly after that. I've used this as an explanation of why we don't use GR later on in our work with the Monte Carlo radiation code, because the radiation that's happening at a region that's close enough to the black hole for GR to be considered is so low in comparison to the rest of it that it's almost not worth mentioning. This is the accretion rates of mass and luminosity through the through different regions, or I guess, yes, this was through the black hole horizon over time. And you can see just the amount of variation that we have in accretion rate. And I am using this later on in the talk, I'll get to this, to motivate the amount of variation that I put on the parameters for my radiative models whenever I'm going between the flaring and quiescent states. That is, if I said there was about a factor of 10 variation here, I wouldn't want to be varying the mass by more than a factor of 10 whenever I'm going from a flaring to a quiescent state with my data later on, because that's not indicated in our simulation. Now, just to give another example of more of the modeling work that we could do with harm, I don't know if the red's showing up so well here, but what I have plotted out, this is looking down from the pole of the black hole. This is just a slice through the equator, and what's done in blue here is synchrotron emission, and what's done in red, which is a bit further out, is the Bremsstrahlung emission. I just wanted to show that this can be a fairly powerful tool for more than just putting together, plots and such. It can make pretty pictures we can compare to observations and so forth. And so, just to do so, I acted like this was M87's disk and inclined it about 45 degrees to our line of sight, and then put on a simple extinction map. So this would be not really a realistic emission map of the region, but you get an idea of what we could do with more time spent with this tool to put these together. Now, that's the first tool that I use. So I have a large-scale GRMHD code that puts together these core models of accretion disks and the beginnings of jet formation for AGNs. What I do with that after I've finished running the harm code, with the library of results that we have, I do a number of runs with our Monte Carlo code, our Monte Carlo radiation and scattering code. Again, this is an axisymmetric 2D code. It deals with Bremsstrahlung and synchrotron emission, and then absorption and scattering, follows the photons throughout the space. What I have depicted here is just an example of what the simulation space would look like. It's a cylindrical code, and we have control over zone number and so forth, and can make this about any size we care to do so. Typically, when we run it, as I've noted, the grid size is slightly larger even than the harm code grid, just because of the amount of time that it takes to run this. For those of you not familiar with Monte Carlo schemes, the idea there is that random numbers are used to determine what happens when given a probability distribution. That is, you have the probability that a photon will be emitted in some energy band, and then you draw a random number and use it to find which energy band you're going to let a photon be emitted in. And you do this 10 billion times and assume that it averages out to what the correct answer would be. Now, to give you an idea of the inputs that go into the Monte Carlo code, as I noted, we have control over the number of zones used. the total region size. We can put in boundary sources. I don't do that for this situation because I'm pretty much encompassing the entire accretion disk area with the simulation region. And we can also use flaring regions, which might be interesting at some point if we decide that there's magnetic dissipation going on at some point in the disk and want to see what happens if we put a flare in at that point and let it act on the particles there. The local inputs, which would be at each single grid point within the simulation, include the electron and ion temperatures, particle density, magnetic field strength, and the electron distribution, which may be some combination or a single Maxwellian for a thermal distribution or a power law for a non-thermal distribution. At this time, we're just doing thermal distributions. It's an approximation, but we're working up to the point where we'll be doing more consistent modeling of the heating of particles in accretion disks. And so we'll be getting to the point where we're putting in our own distribution. Now, the way the code runs is that each zone determines an emission profile. And like I was explaining before, with the random number generation, is allowed to emit a certain number of photons. Each of these photons is called a Monte Carlo photon because it represents a number of physical photons. In this case, we'd probably be using about 10 million photons that we are tracking throughout the simulation volume. But they would, of course, be representing a much larger number of actual photons in this situation. During each time step after emission, the energy and the weight of the photons are changed by absorption and scattering. That is, the photons propagating through the region are allowed to interact with particles or with the magnetic field for synchrotron absorption and processes of that sort. And then the output would include photon spectra, the electron spectra, light curves through time, a fully time-dependent code, and there's photon trajectories, which of course is very interesting because you can then see about what is actually being emitted along our line of sight versus what is the overall luminosity from the region. Now, just to give a depiction here of the two different grids for these codes, what I have shown here on the right is an exaggerated example of the harm code grid. You can see that it's spaced radially and angularly with zones more tightly concentrated toward the equator and toward the horizon. But our Monte Carlo code grid is just Cartesian and cylindrical. So this is what it actually looks like when overlaid with the harm code. Obviously, this leads to undersampling or oversampling, depending on how we have this set up. Usually, both of those situations, really, in order to be most consistent. And this is kind of the way that I have this set. If you remember the pictures earlier with the accretion disk there, this is kind of how I have it set over the accretion disk to cover the region of interest, but not too much of the outflow regions and not over the black hole horizon. Now, just a few comments about how we take the harm output and make it into Monte Carlo code input. All of the output scales to black hole mass and maximum density. That's why for the plots earlier, I have the radii listed in units of black hole mass and so forth. It doesn't make a whole lot of sense until you sit down and look at all the units, but this allows us to then take the same code and use it for Sagittarius A Star, which is 3 or 4 million solar masses, and M87, which is about 6 billion solar masses. And it directly scales just based on what we put in for the black hole mass. And then everything else, or everything falls out once you give it a maximum density as well. As I've noted, we lack a known heating scheme here. We don't know how the electrons reach the temperatures that they reach. And so what we've done in this case is taken the ion temperatures. The ions in this case are heated compressionally as they fall onto the black hole. And we've assigned a global ion to electron temperature ratio. That is, we've said if ions at one location are 1 degree, then we'll say electrons there are 5 degrees. And so ions at another location may be 2 degrees, and the electrons there would be 10 degrees. The global temperature ratio would be 5 in that case. And this is just a way of leaving a free parameter for us to work out what an appropriate temperature would be for the thermal situation we're dealing with at the moment. A similar situation with the magnetic field. what we are actually reading out from the harm output here is what we assume to be the MRI saturated value of magnetic field. And that doesn't assume that there was really much in the way of magnetic field put in to start with. And so if the accreting plasma has a considerable magnetic field, this would simply add to that value that we're getting out. So what we're left with is that we set a black hole mass, maximum density, an electron to ion temperature ratio, and then a magnetic field using that saturation value as a minimum. So those would be our three parameters for just a simple Monte Carlo model. Now, doing that for Sagittarius A Star, I've published a paper with a number of results included, and we'll go over those now before I talk about some of the modifications that I've done to the code to make it more consistent. This first fit is what I call the Bremsstrahlung fit. And the reason for that is that at this bow tie, the X-ray flaring point, this is almost entirely Bremsstrahlung photons. And the reason it fits so well there is that with an LE versus photon energy graph, we have a very flat slope for the Bremsstrahlung emission. Now, that leads to the question, what could we do in this situation to the physical parameters to make this plot or this curve fit the lower energy bow tie? And as it turns out, there's nothing we can do. If we just turn the density down, the temperature down, or the magnetic field down, well, not the magnetic field, density or temperature down, we can get this slope or the curve to go through the bow tie, but not at the right slope. It will always have this very flat slope. And so for that reason, I've said that the Bremsstrahlung idea, which has been presented by a number of other groups, is probably not the most promising one for this situation. There are other radiative components that can reach out to the X-ray, however, and the obvious way to go about that would be to use Compton bumps. That is what I've termed here the second Compton bump. You can see we have a synchrotron curve. This would be the first Compton bump, which would be photons that are scattered out of the synchrotron curve once. And then the second Compton bump would be the photons that are again scattered twice. You can see that the statistics down at this high energy are pretty poor. This was actually a dozen or so runs pieced together to give us this. The reason for that is that the probability of scattering is about equal to the peak values of these bumps related to each other. So you can see that the first Compton bump is down several orders of magnitude from the synchrotron peak. So 1 out of 10,000 photons might scatter there. And then 1 out of those, 1 out of 10,000 of those that scatter may scatter into our second bump, which means that we do end up with these very poor statistics. However, in this case, this does look like a very promising way to fit the lower bow tie because the slope right around this point is pretty sharp and flat, and with a bit of skewing of temperature, we can move where these Compton bumps happen around a bit. And so this is my quiescent fit using that same data. All that I've done between the previous graph, between this graph and this graph, is turn the density down by a factor of 5. That's well within the variability that I was showing earlier with the accretion plots. And you can see that by only doing this, by maintaining the same temperature, the same magnetic field, we drop right down to this quiescent point and manage to fit the slope fairly well. Similarly, I have a first Compton bump fit. You can see that the synchrotron curve is much more extended in this case. The temperature is quite a bit higher. And then it's the first scattered photons that are fitting the flaring points out here. Now, again, this looks more promising because these bumps can be moved in energy fairly easily by varying parameters. So let's look at what can fit the quiescent point. And it turns out that dropping temperature by about a factor of 4 does just that. Again, keeping, in this case, density and magnetic field exactly the same. This, however, does not very well fit the points up here. You can see that our second bump, both of these second bump plots tend to hit a fair number of the radio IR points, whereas the first bump is fairly far away for both of the trials. For this reason, I've suggested that our second bump fit is the most promising, and I think the most likely to be at least close in parameter space to what is actually going on in Sagittarius A Star. I should point out that some of the lack of fit here in the radio is because our simulation volume is just fairly small in comparison to what would be necessary to fill this in. That's been posed through a number of papers and is reasonably well accepted that if I let the simulation extend out to several hundred times what it is, we would probably fill in these points, but it's just not feasible for this study. All right, so discussion of the fit validity. And what I was using to do this, my first note is for the Brimshalom fit, that there was no way that we could make it fit the quiescent point reasonably, given the parameters that made it fit the flaring point. So I've kind of thrown that out as a reasonable possibility. The second Compton bump fit, which we've called our best one, like I noted, is well within the variability that Harm shows with a density drop of 5 to suggest an overall mass accretion change. That is, the plasma that is flowing into the accretion disk may due to the environment that the black hole is passing through or some other situation, may drop suddenly. And that could, I've shown, explain the variation in the X-ray point. The first Compton bump fit is good, a good fit, but not quite as promising because of its lack of fit to lower energy points. Now, we have to step back at this point. This is my master's paper, and say, how consistent are these results? What are the main problems with this? And the most obvious one is that the electron heating mechanism is misunderstood or not well understood. It's expected that magnetic energy is turned into particle heating in some way, and electrons are heated up through that conversion. But without knowing that, and just using the thermal distributions that we've done for this situation, we can only really call this the first approximation. And secondly, what really stood out to me was that in accretion disks, we're dealing with extremely energetic phenomena. And the magnetic fields and velocities in that case are going to be highly anisotropic. That is, magnetic field strength will not be the same in each direction. We can't assume that plasma is flowing the same velocity in each direction. And so we have to ask ourselves, does Harm show this the anisotropy of these parameters as well? And indeed, with this plot that I've done from the Harm data, you can see these are all ratios over a radius. These are just ratios of different, the lower ones here are the magnetic field values or components related to each other, and these are velocity values related to each other. But what you should mostly pay attention to is this is a line at 1, and not much happens around 1. Usually the components are distinctly different from one another. And what that would lead to is very anisotropic radiation from those regions, which was not considered in the first case. And so we have to go in, make some modifications to the way the Monte Carlo code works. The simple modification in this case was changing the way that synchrotron emission is done. And that is letting it be based on what the angle, which is the theta here, and is plotted out here, what the angle is between the magnetic field and the propagation of the electron that is emitting the photon. And you can see that, this angle is actually the angle between the photon emission and the magnetic field. So you can see this is peaked at about 90 degrees, and so the synchrotron emission is highly biased to be emitted perpendicularly to the magnetic field direction. If this is the case, with such high anisotropy, then we would expect to have very distinct radiation characteristics in this region. The plot shows just how the angle of emission changes based on a couple of different values of magnetic field and photon energy. Now, I'll skip over all the dirty details of adding this into the code and talk about the results. This is a one-zone trial of a Monte Carlo code with very simple parameters input. And the idea here is that I put in a magnetic field that I called purely radially. That is, if you're looking down from the pole at the accretion disk, all the magnetic field lines radiate like bicycle spokes away from the black hole. And there aren't any, there's no vertical magnetic field and there's no toroidal magnetic field wrapping around the black hole. And you can see, if we look on the polar angular bin, that is, the photons that are escaping along the polar direction, we get a much stronger curve in the synchrotron than we do for the photons escaping along the equator. And that, of course, is because the emission angle is biased toward that direction. Now, it's equally important to notice that the Compton bump here, which arises from these synchrotron photons, and the Bernstein emission down here are still isotropic. They are not heavily influenced by magnetic field directionality. And so this is a promising first test, and was a good point, or a good way to see that the code was doing what I wanted it to do at this point. Now we get into a bit more of a messy situation with the velocity modifications here. The first thing I did in this case was to step back and say, okay, at what points during our emission and scattering code do we need to think about what the plasma is doing? What do we need to think about how the plasma is flowing? Well, the first case would be whenever the photons are emitted. They would be boosted and beamed in the direction of travel. That is, a moving population of plasma will emit radiation in the direction it's flowing mainly, and that radiation will be more energetic than it would be otherwise. It is boosted and it is beamed in that direction. Now, once the emission has happened and photons are propagating through the region, there's a scattering frequency modification that needs to be taken into account. That is, with a moving medium, photons will scatter more or less frequently depending on the direction they are flowing, whether it's head-on or they're following the plasma. And I'll get into the math of that in a moment. And then thirdly, a scattering angle modification. That is, if we know that the population is mostly moving in one direction and a photon is coming in behind, it's mostly going to be hitting the electrons, kind of a tail-on collision. It won't have a great impact on the scattering angle, and vice versa for head-on situations. And as I've noted here at the bottom, the code in this case operates in the black hole rest frame. And so the way that I've considered this is by keeping all the calculations in the black hole rest frame. And so now getting into some of the math involved. For the photon boosting and beaming, this is the most simple idea. And the suggestion here is that we have a moving body of plasma, and in the frame that is moving with that body of plasma, it looks like the photons are being emitted in all directions. But if we're sitting with the black hole and watching this happen, the photons will be boosted and beamed forward. The way that they are beamed, that is how the angle of angle of emission changes between the co-moving frame and the black hole frame, is based on the aberration of light here, the relativistic aberration of light. A pretty simple formula. And then the beaming is done with the relativistic Doppler effect. And so photons emitted forward for the population of electrons will have higher energy. The angle from the direction of the plasma's propagation will be smaller. And then you can see the opposite is true for photons emitted backwards. They can actually lose energy because they're being boosted forward. And this angle becomes quite a bit larger than you see it would be in this situation. Now, a single zone trial, obviously, again, the place to start for this. So what we have here, the black curve is just a single zone trial done with no velocity. Now, the red curve is a single zone trial, the same trial done just with this one modification included. And so we have boosted and beamed photons. And mostly what you see is that everything has increased in energy about a comparable amount. And that's essentially what this modification does. Without looking at it with angular bins, we can't see much more of a change. The second adjustment is the scattering frequency adjustment. This is a bit more convoluted to think about, but imagine a photon propagating into a box of plasma. If the box of plasma is moving against the flow of the photon is going to encounter an electron sooner and scatter sooner. And vice versa if the plasma is flowing in the same direction as the photon. And you can see, in this case, the nu is a frequency, the scattering frequency, and the way it's adjusted. Again, just a simple formula based on the velocity. And now we can see what happens with our single zone trial whenever we do that. Now we're going from the red curve to the green curve. And what happens in this case, we have a single zone trial, and so we put in a velocity, everything is being boosted and beamed in the direction of travel, but what that means later on is that those photons will then be traveling along with the plasma essentially. And so they're going to scatter less frequently. And so you can see this first scattering bump is significantly down, but after that, everything is pretty evened out in angle, and so the rest of the bumps are equivalently down. The last modification is a bit more complex, and this is the addition of velocities in order to determine appropriate scattering angle. The idea here is that if we have an isotropic distribution of electrons in the black hole frame, we would have an anisotropic distribution of electrons in the scattering frame, in the rest frame for the black hole. And so by adding up the velocities of the total moving population, which in this case would be V based on these equations here, and then the U's, which would explain the electron's momentum, we can get a total momentum distribution in the black hole rest frame. Now we can add that in and include all three modifications. So what we're really looking at here is the orange curve. It very closely follows the green curve, the difference being that for this second bump, where I noted previously that everything got evened out in angle after the first scattering, in this case, that doesn't happen because most of these photons are having tail-on collisions. That is, they're chasing down the electrons they eventually hit. And because of that, their angle does not change significantly during a scattering event. And so the second bump will be even weaker, and so on and so forth down the line. And so we can say our velocity modifications here are working quite well as expected. This brings me to talking about the jet modeling that we're going to be doing. This is very applicable to what I've just been discussing because, like in accretion disks, jets have both very high velocities and highly anisotropic magnetic fields, but more importantly, the velocities are typically in a single direction. All of this is flowing in one direction. So like with some of the stuff we just saw, the scattering depth would be greatly reduced, the scattering frequency would be greatly reduced, the photons would be very beamed and boosted, but would tend to escape the region with much less scattering than if this was not considered. What I have shown here is an MHD model that a group in Europe has done. They're sharing their data with me in order to run through my code because we have the capabilities to do what other groups aren't able to with this velocity modification. And this is actually just a velocity map to give you an idea of some of the Lorentz factors that we would encounter in these situations. This matches very well to M87's jet. And you can see that in this case, it gets up to a Lorentz factor of about 14, which is 99.6% of the speed of light or so. And at velocities like that, a lot of scattering will be damped down. As I've noted here, this paper was actually written to show how magnetic collimation was able to govern the jet's direction. And you can see indeed how things tend to kind of bunch up along the edges of the jet here. And in fact, what happens is that the magnetic field is, the pressure increases on the skin of the jet as the plasma is flowing outward. The pressure builds up at that point, and you get a buildup of density and magnetic field along the edges that help show the limb brightened, the edge brightened structure that we actually see from the synchrotron emissivity of M87 in observation. For this system, or this situation, I wanted to do a very quick, simple test. And so what I have shown here is essentially a one-zone disk and a two-zone jet model. And I've asked myself, if I put this system together, what impact will the jet have on the disk and vice versa? That is, what reprocessing will be done by the jet of the disk's photon and by the disk of the jet's photon. And if you just think about this intuitively for a moment, as I've noted here with the arrows, these jets are flowing constantly away from the disk. And so because of that, you would expect that any photons from the disk that reach the jets, they're not going to scatter very frequently. And the photons from the jets will heavily be beamed away from the disk, and you don't expect a whole lot of interaction there. But I wanted to see if this is true in order to state whether it was reasonable to separate these and do separate jet from disk trials and vice versa. And so if we take a jet system without a disk, and we take a disk system without a jet, and put together the spectra of the two regions, what we get is this green curve. So this is the SED from the jet system added to the SED from the disk system, but they're not in the same system at this point. The black curve is when they're put in the same system. And so you can see the change in the total luminosity, particularly in this region where we'd expect a lot of scattering to happen. Now, in this case, this is no velocity. And we have a fairly large interaction, so we could say that if jets weren't flowing with any appreciable velocity, they definitely need to be considered with the system, because this red highlighted region is what we get by putting them together. Now, if we take the same trial, the same exact trial, and just turn the jets up to about a Lorentz factor of 5, which is a fairly modest Lorentz factor for the situations we're considering, you can see the interactions quickly diminish. And as I had just shown you in the previous map, we were talking about Lorentz factors up to 14 or so. And so for that reason, we've said that it is reasonable to separate these systems. That is, it is reasonable to have a smaller disk model and then a larger jet model, and don't have them interact with each other at all. The other problem that we had with consistency with our first batch of results was with the electron heating mechanism. Now, my advisor, Edison Liang, has done some interesting work recently using particle and cell simulations. This is very, very different from the very large-scale simulations that I've been showing you. The idea being that you take, for his situations, 10 to the 7 to 10 to the 8 particles, you put them in a box and you see how they interact with each other and magnetic fields, essentially. It's governed by Maxwell's equations and the Lorentz force equation. You can see just a couple of the typical parameters here. But what this has shown, and these are results, is we have a black curve here that is an early time electron distribution versus gamma, which is the Lorentz factor. And then these other curves are later on in the simulation. And what you can notice here, if you look closely, is that we have two distinct slopes at these high energies, one right around here, and then another sharp or less slanted slope out here. That is indicative of, in the high energy tail, of having multiple Maxwellians. That is, each of these slopes would correspond to essentially a thermal distribution with a different temperature. And so this is very promising. This is done using accretion disk appropriate situations parameters. This is very promising for us to be able to put back into our Monte Carlo code a reasonable electron distribution, which may be appropriately modeling that of an accretion disk. However, whenever we look at this, there's a bit of an inconsistency just in the scale sizes we're dealing with for all of our simulations. What I've put together here is what I just called magnetic turbulence level. This is an artificial line I put in, which could be an ideal magnetic turbulence line. But the most important thing is that I have the length scales of our codes plotted out here. And you can see that over here on the far right, we're talking about the very global simulations, the Monte Carlo and GRMHD codes. And then way over here on the left, a number of order of magnitude smaller, we're talking about the PIC simulation. And we would argue that particle energization happens from about this point and at smaller length scales in an accretion disk. This would be about, this 10 to the 3 centimeters would be about the largest electron gyro radius around the magnetic field line, which is how we expect that these particles are gaining energy from the magnetic field. And so if we're saying particle energization happens down here, and we have a PIC code covering some of that, we can't really say that the turbulence, if we see this level of turbulence in our global simulation, and then our PIC code says there is this level of turbulence, can we really say that this is a continuous spectrum of turbulence that would cascade down into particle energization? So essentially what we're saying is, does this turbulence remain consistent over such a large gap in this simulation space? In order to fill that space, what I've started working with recently are shearing box approximations. This is a very interesting way of doing MHD simulations, where you put yourself, essentially, you put your simulation into a co-rotating box. That is, we have a box of plasma that is orbiting around a black hole. And we're kind of riding along with it, seeing what it does as it does that. And so what we end up with, we have the x direction here is the radial direction, the azimuthal is y. And so you can see this velocity that they've set up, what they call the shear velocity, is only dependent on the x value, but only in the y direction. This is called a shearing velocity because if you can imagine this situation, if you're sitting in a box with its origin at x equals 0, right in the middle of the box, then on one side of that, this is going to be negative, and on the other side of it is going to be positive. So you'll have essentially azimuthal velocities in this box that are going across each other, that are shearing. There are a number of limitations to the shearing box approximation. I won't get too much in depth with them because they're not pertinent for our situation, but just to show that we've covered them. You don't want the spatial extent of the simulation box itself to approach the radius that you are saying it's orbiting at. That makes sense because we're trying to keep this a localized simulation. And we can't calculate global properties of the disk from this simulation. That is, we can't take our harm data, put it in here, and say that we're now getting some different accretion rate through this point. But it is useful for finding at specific locations, specific locales in the disk, what particle energization looks like through time and what the electron spectra that we get out would turn out to be. This is just a pretty picture of a shearing box simulation that was done by the Athena MHD code, which is what I'm using. I'm modifying it for my purposes, but just to show this on the left panel here is a magnetic field. This slab is a density plot, and I think this might be a velocity on the other panel. But just to give a shout out to the group that made this code, it's very useful, and I expect that I'll be able to get a number of results from it. This is the math that goes into Athena's shearing box. I won't get in too much in depth with it. You can see our shearing velocity here again. Of interest above that is this Q factor, which is called the shearing factor. And you can see it's related to the derivative of the angular momentum or angular velocity with respect to the radius. And that just is simply saying how much shear is happening in the box. Pretty basic, the ideal MHD equations and the internal energy equation and equation of state allow it to evolve through time and follow the results. The specific boundary conditions for the shearing box are pretty interesting. What you can see here, the middle box would be what we're calling our shearing box. The outer boxes are ghost boxes that are allowed to slide alongside of our shearing box. So you can see the idea here that if we have this one box in the middle that we're sitting with, if the velocity of the plasma outside is higher in one direction and lower in that direction interior, you'd have boxes sliding with respect to the surfaces of your main box that you're watching. And essentially what this sets up is that at the edges of your boundary, we just have more of the same sort of stuff. So if the code is trying to decide what flux is happening to this surface, it essentially looks at our original box and says, okay, there's a box that looks just like it's sliding along next to it. We use that to calculate the flux through these surfaces, use that to determine what happens to the density and the magnetic field in these locations. In front of and behind the box and on top of the box, which are the non-shearing directions, we are essentially saying the same thing, that we have these same boxes stacked up there, but they don't have the same shearing boundary condition. That is, they're not sliding along next to it. They're just periodic. Now, this is the setup for a very simple test of the shearing box approximation. What I have shown here on the bottom is that in this case, R is outward to the right. So somewhere over here, we might have a black hole. Z is the upward direction. So we're kind of looking at a cut through like the plots that I had shown of the full accretion disks earlier. The colors are a similar situation, with dark red being the highest and dark blue being the lowest. So you can see here, I've called this the azimuthal velocity. That's the shearing direction, where you can see the dark red is the highest value. Gray is the median value, which in this case would be 0, and blue would be the lowest value. So you could consider that these dark red locations are flowing into the board, the dark blue locations are flowing out of the board, and that gives you an idea of how the shear is happening in our box here. A sinusoidal vertical magnetic field applied here, and then the density perturbations are just allowed to be random, so it just looks like a bunch of specks up there. Those are all within a couple of % of each other, however. And so now, for a first test, we just let this evolve through time. Okay, I guess they're both running now. What we have on the left is a density plot using the same colors that were shown previously. On the right is the velocity perturbation plot. So what that would be is sitting in the box. Again, the dark red may be flowing away from us, the dark blue would be flowing toward us. And you can see that the locations of dark blue tend to be falling to the left. The locations of dark red tend to be going outward, and that's because of their respective velocities to the box, that they're displaced because of their angular momentum. These are the same trial. They're not really running at exactly the same time now, but it's interesting to see how things match up with the density and the velocity perturbations. What actually tends to be the case is that the very lowest lowest density regions correspond to the points that are sitting with the box, that are at zero velocity with respect to the box. And so they're moving just kind of considerably around with the box. Now, since we're talking about taking this situation and we're talking about doing this situation down through a number of orders of magnitude in simulation space, it's important to see how the resolution of the problem changes things. These are exactly the same trials, set up exactly the same way, except that on the left we have a 64 by 64 zone. That is, there are 64 boxes vertically, 64 radially, and then 128 and then 256. And so you can kind of see the differences in qualitative development here. What's of most interest to me here is that these are all scales of the same values, the colors are. So you can see there is not a whole lot of red or blue in the lower resolution boxes. And so we're not getting the same regions of very high flow just because of the lower resolution. And that suggests that in order to do this consistently, we need to be approaching it with whatever the highest resolution you can reasonably run. I haven't done full tests with this, but you would expect there would be a point of diminishing returns where the extra computer time would not be worth the amount of increased resolution we get. But then the idea here, and what I've put together, is that we can put together an entire turbulence plot using all of the different trials. And this was just doing that very basic test that I just showed. And yet you can see, if you look at the turbulence plot here in black for the very low resolution case, it follows a pretty linear, it's pretty linear in log space here. And then we come to the red one, which is the next least resolute test, which extends a bit further, and the green one, and then the blue one. You could see if, when put together, they tend to build on one another in such a way that we could say the turbulence from the black one could be extrapolated out to explain the turbulence from even the blue one. And that's the hope in this situation, that the same level of turbulence we're seeing on our full-scale harm runs, which are over 10 to the 20th centimeters or so, we're hoping that the turbulence at those scales will at least qualitatively look like the turbulence at the very low scales when we take that same data and run it through these other tests. And so, of course, the next step is going to be to take actual harm data and run it through the shearing box approximation and see what happens. I haven't gotten very far with this. Mostly I've just put up these pictures to give you an idea of what happens when we zoom in here. You can see that the grid size becomes very important. And what we're seeing here is the harm grid size, actually. These are much more resolute images in the shearing box, but we're dependent on the harm size. And so there's some consideration about whether we need to do some interpolation to smooth things out or not. So I wanted to do some tests like this to start out. And so if we turn this on, we can see how the velocity perturbation evolves for the few seconds that I was able to get this to run. And the most interesting thing here is that even late in the simulation, you can very distinctly see these lines that are running through that you can see at the very beginning. And so that leads to a number of questions about doing this consistently. Okay. For this situation, do I need to interpolate the data? Do I need to smooth everything out? Is there a way to make it run without ending up being dependent on the original grid size at a late time in the simulation? Another thing to consider is whether the density perturbations are too large. As I pointed out with the previous test, the density perturbations they put in were about 2% or so. In this case, these can be orders of magnitude that these are ranging up and down. And it just may be that this isn't an appropriate situation for this. But with some trial and error, I've managed to at least get the movie I showed you previously, and so I'm hopeful that there will be more results coming out soon. Now, just to give you an overall idea of what my research tasks are for the next year or so, I will be doing large-scale core simulations of M87 to put together emission maps to constrain spin value, global temperature ratio. That's kind of going on now. At the same time, I'll be doing these very large-scale Monte Carlo models of M87's jet, and with an intent of showing even more realistically that we don't have to consider the jet and the disk as an entire system, that they can be taken separately for greater consistency. Then, as I was just talking about, I'll be doing these progressively smaller shearing box simulations. That is, I'll be zooming in to cover this simulation space, this gap between our large-scale global simulations and our very localized particle and cell simulations. And then the final step would be reapplication of the PIC and shearing box results, which talk about how electrons are energized and heated in these regions, to the Monte Carlo situation in order to more effectively or more consistently model the global spectral energy distribution of these sources. And with this, I hope to put together kind of a suite of codes that is fairly easy to use and adapt to different low luminosity AGNs, and can be at some point kind of put together and create an entire library of these sources that are available and parameters. And so that brings me to the end of my talk. I'd be happy to answer questions now. Yes, sir.
I have one about, does it use fractal, where you have a triangle and then you divide it into 4 triangles, and then each triangle again is divided into triangles for the simulation, or just nothing used for graphics or making bodies and shapes and everything? Because this didn't seem like this was fractal now.
It certainly could. I'm not sure if there's a real direct correlation, but I do see that it could resemble that.
Well, if they get closer to like a curved space-time.
Mm-hmm. Certainly. And most of these, like the localized simulations that I'm dealing with are considerably far from the black hole, that I don't deal with them in GR. And so we consider it to be a Minkowski everywhere, at least at those locations.
Did you look at a magnetic diffusivity, which you're already putting in for South?
I have. Again, that's a case of not really knowing what's happening in accretion disks and not being able to apply it so well. I mean, it's an area of interest, certainly, but nothing that I'm working with right now.
You've mentioned the cost of doing more simulations or higher fidelity. Can you tell me what kind of computers you're using, how many CPUs, how long does the simulation take?
I use the supercomputers at Rice, okay. And so usually for our Monte Carlo code, it falls on its face after about 16 processors are added to it. It should be, theoretically, it should be purely parallel, but it doesn't quite work that way. So I will usually run it with 16 to 24 processors. And with that number, we're talking maybe 24 hours to get a full spectrum that's got the second scattering bump included. And it's just a matter, I'll have results that'll show the full synchrotron curve, the full Bremsstrahlung curve, because that's statistically easy to do within minutes. And it's just a matter of enough photons being pumped through the volume then to scatter enough to fill out the Compton curves. The GRMHD simulation for, say, a grid size of 256 by 256, which is typical, will take 3 days to a week to run. But I've done larger scale runs that ran for 6 months and never ended. So it's just a matter of how much you want to do. That, however, there is a parallel version of that out, but I've been running the serial version because that's what I've had for the last 5 years.
What kind of random table do you use for your, is it just a standard random table for month total?
I didn't write the code. It was something taken from numerical recipes, and I assume that it's a very, very standard setup. I couldn't say off the top of my head which scheme it is, though.
Any other questions? Let's thank our speaker.
And there is a sign-in sheet still floating around, so please, if you haven't signed in, please do so. And also, I have, for students who are working on their papers, would like to get another draft of that soon. So you should be working on the, at least by the materials and methods part of your papers. And so please get that to me soon, and email or handing it to me either way. Okay.